Okay, we're going to talk about medians and altitudes. So this is a section where um, includes medians, altitudes, perpendicular bisectors, angle bisectors. But this specific video is going to be talking about medians and altitudes. So to talk about these, we're going to talk about them inside a triangle. We need to define them. So a median is a segment that has endpoints at a vertex and the midpoint of the opposite or the side opposite the vertex. So we have vertices A, B, and C. So what we're going to do is the side opposite vertex A would be this side BC. All right, so we're going to find the midpoint of that. And when you connect those, that segment from the vertex to the midpoint of the opposite segment, that is the median. That's what they call the median. So we're going to do that to all three, the vertex here to the midpoint of that one. So we're going to get the midpoint of AC and draw a segment from the vertex of B. So that would be the median of that one. And then get the midpoint of AB. And then we'll get the last one here and go from vertex C to there. Now what you're going to find is when I do that, all three of those are going to meet at the same spot. Okay, and we'll talk about what that actually means later on. But that's what the idea of median. All right, altitude. So median should be middle. That should make sense. In probability, you talked about mean median in mode, and median was between, halfway in between. So what this is talking about is let's label this AE. So whatever AE is, whatever that distance is, okay, if E is truly the median, then CE should be the same thing. And it is. Okay, and that's going to happen the same thing with this median, which would be F. So AF is going to be the same as BF. And this one, GCG, the distance C to G is going to be the same distance G to B. Now, what you're going to see sometimes instead of actual measurements is they're going to have these marks. So that being one mark and that being one mark, that tells you that E is in the middle. And they would do the same thing here. You would have 2 marks A to F, 2 marks F to B, and the same thing for this one. So if you see a diagram that has that, that's all it's telling you is that that point is a midpoint, and if it connects to the opposite vertex, then that is a median. Okay? Altitudes, it is what it sounds like. You probably heard altitudes in trying to find the area of a triangle. But altitudes is a perpendicular segment, which in previous lessons we've talked about what perpendicular means, right? It's got to be 90 degrees. A perpendicular segment from a vertex to the line containing the side opposite the vertex. So it's the same idea with median. I'm going to take this vertex and I'm going to make a perpendicular line with that opposite side. So all I'm going to do is I'm just going to construct a perpendicular line. That is perpendicular to that. So I'm going to construct that little segment there. And that would be the altitude from vertex A to opposite side BC. And we're going to label this, instead of B, we're going to label it something else. All right, now if I do that to all three of those, we'll go from B and draw a perpendicular line to the opposite side. Well, that's a little off. And we'll talk about why that is what it is later. But that would be the altitude of that one. We'll make it a different color. And then let's do this one, make a perpendicular. And there, so that would be the altitude of those. All right, and as we move this, we'll talk about later on what it actually means and what we're actually trying to find from that. But that's the definition of altitude. So you got the definitions of median and altitude. Now we can move on. So Point of concurrency of medians. So the point of concurrency, what that means is the point where three or more lines intersect in one place. And we just saw in the previous slide right here where these three medians meet. This is going to be the point of concurrency. So specifically what that's called is the centroid. So the point of concurrency of the medians is going to be the centroid. So for example, let's go ahead and do this one. These are the midpoints of those segments. And if we do like the previous slide, and we construct the medians, there's going to be A to F, right, and B to C, and there is C to H. So this point right here is where the medians meet, the three medians meet, and that is called the centroid. Okay, now, here's why we need to know that. If we take, let's say the distance from A to the centroid, so from the vertex to the centroid, and we measure that, that right now is 5.970. Not important right now, but let's compare that to the length of the whole thing. Okay, probably doesn't mean a whole lot right now. Let's do it to the rest of them and see if we can see a pattern. So that's from the vertex A. So let's go from vertex B. So B to the centroid. All right, that's going to be about 9. All right, this program rounds pretty close. And the distance of the whole median is going to be about 13.5. So that's B. Then we'll go from C to the centroid. Compare that. D to the midpoint of the opposite side. Compare those distances. And that's what I have. Now, it may not look like anything right now. It may be hard to see a pattern. But as we start manipulating this, I want you to understand this. Right now, you have an acute triangle. If we did all the angle measurements of A, B, and C, they're all acute angles. So that would be an acute triangle. So pay attention to the centroid as I manipulate this triangle. That's about a 90-degree angle, right? A, B, C. I wouldn't want to assume it is, but that's pretty close to a 90-degree angle. But watch what happens when I make obtuse. This is an obtuse triangle. Now, if you pay attention to the centroid, no matter where I move this thing, and I'm just moving vertex A, I can move the other vertex if you want to. Either way, and you can make that acute, obtuse, whatever. What you're going to find is I don't care where you move this thing, right, acute, obtuse, whatever the angle measurements are, the centroid is always going to be in the middle. And that's important because when you start talking about the other three, you start talking about the orthocenter, which we'll talk about, and the other two. That's important to understand kind of what the difference between the four are. Okay? All right, so let's look at the measurements and compare the measurements. It's kind of hard to see because they are rounded. But here's what you basically need to know centroid for. If I compare these two measurements, and let's just calculate this. From A to the centroid, right, this length right here was 6.28. If I divide that by the whole thing, here's what I get. Now it's 0.7. It rounded it. I'm going to change that to see if it can round it to something a little more than what we can see. We'll round it to the thousandths, so it's that. And let's do the same thing for B, and then do the same thing for C and see if there's a pattern. So I'm going to divide that by the whole thing, and I get 0.7, the same 0.7, which again, we're going to round it to the thousandths. So I get the same thing. Well, if the same thing happens to C, then I got a pattern going. So I'm going to do the same thing. All right, C to the centroid, and then the whole length, compare that, and I get the same thing. All right, so how does that help me? Well, this program does decimals, but if you think back, 0.667, again, that's rounded, so really that's 0.6 repeating. As a fraction, that's 2/3. So the reason we talk about centroid is on all of these, right, it's consistently 0.667. From the vertex to the centroid is 2/3 of the way, or 0.667, third of the way of the whole thing. Okay? And where we're going to need this is down the road a little bit when we talk about putting this in a coordinate plane. So we got to know the basics in order to do the coordinate plane. But when we talk about partitioning a segment, we've talked about that in previous. This is kind of an idea with that. So the conclusion we have with a centroid, right, dealing with medians, the point of concurrency of a median, is that the distance from the vertex, which A, to the centroid, is 2/3 the distance from the vertex to the opposite midpoint. Okay? And then, like we did before, no matter how you move this thing, whether it's acute, whether it's a right triangle or it's an obtuse, it's always, the centroid is always going to be on the inside of the triangle. That's important for later on. Okay, and the question always comes up, okay, all right, but when are we ever going to use this? Centroid is actually used more often than I think people think. Couple of situations. Right here, this person, you got a triangle block, which you could get from construction to find the center of that. You can see they use centroid to find the center to prop that piece of wood up. I know probably everybody's seen this, where people have a human square. I know you're not going to calculate the centroid, but you've got to have a center of gravity. So at any point, you need the center of gravity, which is used a lot in engineering. So if you plan on being an engineer, this is not the last time you're going to hear the word centroid, whether it's mechanical engineering or others. So there's a real world application of what a centroid is actually used for. Okay, so just to understand, the centroid comes from the intersections of the medians. All right, so at the first we talked about altitude. So orthocenter is going to be the point of concurrency of the altitudes. So if I do all the altitudes of A, B, and C, where those three altitudes meet, is going to be called the orthocenter. All right, so we'll do these real quick. Altitudes, again, I'm going to go from A and draw a perpendicular line through CB. I'm going to go from angle or vertex B, draw a 90-degree angle through AC. I'm going to do the same thing from C and draw a perpendicular through A and B. So when I do that, this is what we get. Okay, so if you're not sure, here is proof that BCA, which is this angle, is 90 degrees. That is perpendicular. AEB, which is this one, is 90 degrees. That's perpendicular. And so is CDA, which is this one right here. And no matter where I move this, you're paying attention to these. These are always going to be 90 degrees, no matter where I move this thing. So that is truly perpendicular. And so those are altitudes. Those are true altitudes. All right, so let's look at where they intersect. They intersect right here. All right, that is called the orthocenter. Okay, so you're going to have circumcenter, which we'll talk about in another video. You're going to have incenter, which is also going to be in that video. You have centroid and orthocenter. And it's going to be hard to understand the difference between the four. So it's really important to write good notes. So what's going to happen here, where we learned over here in the centroid, that no matter what this moved, it was an acute, right, obtuse triangle, centroid was always going to be in the middle. Let's do the same thing with orthocenter and see what happens. So right now we have a acute triangle. All these angles are acute. And as I move this and I keep this an acute triangle, what's always going to happen? Well, that orthocenter in an acute triangle is always going to be on the side. But I think you see, as I keep moving, that thing is getting closer and closer. Now, let's say that is a right triangle. All right, well, where's the orthocenter now? It's on that angle. It's on that right angle. It's not just on the triangle, it is on that right angle, which should make sense because that's what an altitude actually is. Back in the day when you did area of triangles and you had to get altitude in order to get 1/2 base times height, that's what it was. It was 90 degrees. Okay, So acute is going to be inside. A right angle is going to be on that right angle. A right triangle is. Let's look at it in obtuse. So if I make an obtuse, right, there is a right angle. And if I keep going and making an obtuse angle, this obtuse triangle, now all of a sudden the orthocenter is going to be on the outside. Well, is that true on all time? Yes, it is. So I got a right, I got an acute, right? Orthocenter is inside. And once I go obtuse, now that thing's going to be on the outside. Okay, so that's an important idea to understand about orthocenters. So really right now, the only thing about orthocenters that you really need to know is the orthocenter is inside in an acute triangle, on the right angle of a right triangle, and outside of an obtuse triangle. Now, to be honest, there's not a lot of usage in the real world with the orthocenter. There are a few, and we'll take you to this site real quick. And if you go to this site, it'll show you an example of constructing a hang glider. Obviously you want to have the same links and all that. So that's a real world application for that. Not used as much as the other ones, but it is used, and I've seen it used in circles as well. So, but there's a video on orthocenter at the point of concurrency of altitudes. Altitudes go with orthocenter. Centroids, right? That's the point of concurrency of medians. And just a couple examples of how they fit in the real world. The next video is going to be a video on in-center and circumcenter that go with this. And hopefully as we combine this, it'll help you understand how all four are related.